Hi, it's Major Rayhan, and I will be talking to you about momentum and impulse. So physics is the science of how things move. In kinematics, we talked about the relationship between displacement, velocity, and acceleration. And then we moved on to Newton's laws. And we talked about how a force impacts the acceleration of an object, or how it changes its motion. We also talked about kinetic energy. How can we describe the motion of an object based on its speed and its mass? We saw that kinetic energy was incredibly useful when we do conservation of energy. But it wasn't the entire picture, and that's why we're going to talk about momentum. Momentum is a description of the total quality of motion of an object. Not only do we have a magnitude describing how it's moving, but we also have a direction describing the direction in which that object is moving. So of course we're going to use a vector for momentum because it has a magnitude and direction. The definition of momentum, which we'll use a lowercase p, always with the vector hat here, is the mass of the object times the velocity of the object. It's important to preserve that vector nature of movement. All right, so let's take a look at what it means. I have two masses here that are identical in mass, and I'm going to apply the same force to both of them. Call that force F. I'm going to change, however, the amount of time over which I apply that force. So the first object will have the force applied for some time t. The second object has the force applied for some time 2t. Now, the force applied to an object is going to give it an acceleration, and therefore it's going to change its velocity. So let's say both of these were at rest. We're going to have some velocity in this direction, in the same direction that the force is acting. The object has a mass, and it has a velocity, therefore it has a momentum. Same thing down here. Except in this second case, the momentum is twice as large as it was in the first case, because the force was applied for twice the amount of time. So we see now that there's some kind of relationship, and in fact it's a direct correlation, direct proportionality between momentum and time, and momentum and the force that's applied. This could be very useful given certain information in a problem. How do we compare, or how do we talk about the difference in momentum after the force was applied and what the momentum was initially? Well, we need an intermediate quantity for that, and that's impulse. We use an uppercase J, and it has units of Newton seconds. All right, so let's look at our object here in this first case. We started off with a momentum of 0 because it was at rest, and then we give it some momentum p. And when we do delta in math or engineering science, it's always final minus initial. So the change in momentum here was momentum p minus 0. So the change in momentum in this case was simply p. We can use this equation and rewrite impulse in terms of mass and the change in velocity. So we're making an assumption here that the mass is going to be unchanging throughout the entire process. So I could pull that out of this term, and we'll just look at the change in velocity over some amount of time. All right, I was talking about forces, I was talking about times. How do we actually relate those back to momentum? Well, if I have some force, some time-varying force, let's say a foot kicking a soccer ball, and I look at a tiny little infinitesimal time when that foot is in contact with the soccer ball. I'm going to call that dt here. I look at the time over which that force was applied. We're given a differential impulse. So there's been a tiny amount of impulse applied on that ball because there was a force applied over a tiny amount of time. And now we can see where the units are coming from here. All right, that's kind of helpful. Let's look at the total impulse. Of course, the total impulse, if we have a little differential impulse here, is just going to be this term. And we'll make the limits of integration our final time and our initial time. And now we know what the total amount of impulse was, let's say, on the soccer ball from the foot kicking it. Okay. All right, so we have a total impulse. Now if I take this differential impulse, which I know is equal to the time-varying force function by differential time, I'll put that right here into the integrand. And we come out with equation 9.3 in the book. So we see the total impulse applied to some object by a force is equal to the integral of that force from some final time to some initial time. That's kind of useful, but often we aren't given what this force function was. We don't know what it is for a soccer player kicking a soccer ball. So we have this definition from calculus that says the average value of a function is equal to the integral of that range of the variable of integration times the integral of that function. We can use that to find out what the average force was. So here we'll take our force function. We want the average force. So it will be multiplied by the inverse of the time that we're looking at, time final to time initial. There we go. Look at this. This integral here and this integral here are the same. So we know that this term is equal to total impulse. And then I can just move this delta t over, and I know that the average force, my vector hats there, I know that the average force multiplied by the time over which it was applied is equal to the total impulse. So now we have our definition of how to use impulse and how it relates back to momentum. I think that will be it. What?